Well, welcome back to Engineering 201. We're continuing to do our work with node analysis. And we started that last time. Normally in a face-to-face lecture I might back up and maybe even rework that problem that we did last time. Fairly simple introductory problem. But with the beauty of videos, you can go back and rewind that and look at that. So I might direct you to do that. If this lecture makes perfect sense, great. If you're struggling with some of these comments or concepts, go back to the video prior to this one and watch the end of that one, and that's the introduction of node analysis. Well, with that, let's see if we can tackle this problem. We're given a fairly typical node problem. We would recognize this as having three essential nodes, an essential node there, an essential node there, and one essential node across the bottom. We'll go ahead like we've always done and take this one at the bottom as a reference node, reference ground to that. And I might talk about this then as node number 1, and I could put voltage 1 there. That would be the voltage at this node with respect to this one. We usually just indicate it as V1, but we could say actually V1G if we wanted to. That's the voltage here with respect to this reference ground. And then likewise we would have a node 2 right here, and we would say that this would be V2, the voltage at this node with respect to ground, or this point here. This entire bottom is all one node. Now some of you might be thinking this is a node over here, or that's a node. Indeed it's a node, but not an essential node. So we only have 1, 2, 3 essential nodes. 3 less 1 is 2. We'd expect to need then 2 independent equations to solve this problem. A interesting thing here too is we have, and I don't know that we've tackled too many of these, we have a current controlled voltage source. So the voltage over here with this current controlled voltage source is given as 8 times whatever this current I phi is right here. So whatever this current comes out to be, we multiply it by 8, and that would be the voltage there. So that'll be a little added complexity for this problem. Well, I'm going to go ahead and assume some currents so we can work on this. Why don't I take this current as I1. I'll say that's I1. I'll go ahead and take this as I2. That's already labeled as I phi. That's fine. I'll go ahead and take this as I3. And finally, we could take this as I4. And there's really no rhyme or reason to putting those in. A lot of times, just out of habit, I will end up putting them leaving the node, although I didn't do that with I1 and I4. But that should be fine. So if you draw I1 leaving the node, your equations are just going to differ by a negative sign. So I just put those in fairly arbitrarily. So if I then use Kirchhoffs current law at node number 1, so looking at Kirchhoffs current law right there, what can I say? I can say that I have I1 going in, and then it's going to split off to I2 and I phi. So I1 is equal to I2 plus I phi. Okay. And then what we'll do, let me double check that, I1, I2, and I phi, yes. So then we'll write I1 and I2 and I phi in terms of our voltages V1 and V2. Let's see if we can do that. I'll find this voltage here that goes, the polarity goes in the opposite direction of this current I1. So to get from there to there would be the same as going down here, which is minus V1. So I'll have minus V1. And then this is 0, and then back up there I would have a gain of 20. So I will say that I have 20 minus V1 divided by 2. Does that work? Minus V1 plus 0 plus 20. And I've written this as 20 minus V1 just to kind of protect that negative sign. If you put it out front as minus V1 plus 20, you tend to lose that negative sign. Now we're going to say that this is equal to I2. I2 is a little easier. I just need to find the voltage that goes this way, which is simply V1. Polarity has to go opposite of I2. So that's V1 divided by 20. And then I'm going to have what? I phi. I have to find the voltage that way, so it would be going from here to here, which is minus V2 and plus V1. So V1 minus V2 divided by 5. You see that? As I go from here to here, that would be the same as going from there to there, which is minus V2. There to there is 0, and back up to there is V1. So minus V2 plus V1. And you could really say that's a statement of Kirchhoffs voltage law. From there to there to there is the same as going from there to there. Okay, so I've got a nice equation there. The only problem is it has two unknowns, V1 and V2. So we'll have to write another equation. Well, let me do that. Let me look at Kirchhoffs current law at node number 2. And what are we going to get there? We've got I phi coming in. We have I4 coming in, and they combine to make I3. So here we go. I phi plus I4, that's going in, is equal to I3. Okay. Well, we got I phi over here. We know that this is I phi, so I can just rewrite this as V1 minus V2 divided by 5, plus then I4, so I have to find that voltage right there, don't I? Which is going to be minus V2 plus 8 I phi. So 8 I phi minus V2 divided by 2. Does that make sense? Going from there to there would be the same as going from there to there, which is minus V2, and then there to there, which is plus 8 I phi. You could also think of it as the voltage here at the head of this arrow right there, which is 8 I phi, minus the voltage at the tail, which is V2. You treat it almost like a position vector from statics in that regard. The value of the voltage at the head minus the value at the tail is probably not the best way to think about it, but from a mechanical standpoint, it does work. Is equal to then I3 is simply the voltage in this direction, which if you look at that is going to be V2 divided by 10. So I have V2 over 10. Okay, let me double check things here. V2 over 10. Yeah, I think I'm okay. This is going to be a little bit tricky here because I'm going to have to do yet another substitution. So maybe I'll work through that. I could say that I have V1 minus V2 over 5 plus a 8 over 2 would give me 4 I phi minus V2 over 2, I'll do that right, yep, is equal to V2 over 10. So I can make the substitution for I phi. I'm going to have to substitute in there. What is I phi? Well, I phi is that thing right there, isn't it? So I'm going to have V1 minus V2 over 5 plus 4 times V1 minus V2 divided by 5. Sure I've done that. Yep. Minus V2 over 2 is equal to V2 over 10. Well, I think I'll multiply this whole thing by 10 then. So when I do that, I come up with 2V1 minus 2V2, and I have 4/5. I multiply that by 10, that becomes plus 8V1 minus 8V2 minus 5V2 is equal to V2. Is that right? When you multiply this thing by 10, You get 2 of those, 2 of those. 4/5 becomes 2 times 4, which is 8v1. So 8 times v1 minus 8 times v2. Multiply this by 10 minus 5v2 is equal to v2. So I think I will continue on here and group up some terms. I think probably the easiest way is just to move to the next page. And a lot of times on these problems, algebra can be as the most difficult part. So let me keep working on this. Let me repeat this up here. So I have 2v1 minus 2v2 plus 8v1 minus 8v2 minus 5v2 is equal to v2. Double check that. Okay, and then what did I have over here for this equation? Maybe I'll multiply this one. Take and multiply this by what? 20? So when you do that, you get multiplying by 20, you'd have 200 minus 10 v1 is equal to v1, and then plus 4v1 minus 4v2. Is that right? Multiplying this equation by 20, you're going to end up multiplying this term by 10, so 200 minus 10 v1. This would then be multiplied by 4v1 minus 4v2. Could group up the terms if I wanted to here, kind of rearranging things. I would have 200 is equal to, this is going to go over as positive 10v1, there's 11v1, 15v1, and what do we have? Minus 4v2. So I could write that then up here as 200 is equal to 15v1 minus 4v2. So I've simplified those equations and reproduced those on the paper. Equation 1, if you will, and equation 2. And we're continuing to work on those. Like I said, oftentimes algebra is the toughest spot. If you wanted to come back and put these into a solve routine or something like that, you could. You could try and, at the point we're at now, put them into a matrix and solve them if you wanted to. But I'll just keep doing them, probably do them by some substitution. So tidy this one up. What do we have over here? I've got 2v1. 2 more is 10. So I have 10 v1. And then what do I have for v2? Minus 2 of them. Minus 8, which is minus 10. Minus 5 is minus 15. And then one more coming over as negative is minus 16. v2 is equal to 0, right? So I could say then that 10 v1 is equal to 16 v2, or v1 is equal to 16 over 10 v2. Of course, be 1.6, but I think I'll leave it like that for simplification. Now, and we didn't talk about this, probably should have talked a little about what are we looking for. We're looking for the power dissipated in the 5 ohm resistor. So we either have to find the voltage across that or the current going through it, or both of those. So it's a node problem. It's no surprise that we are looking for V1 and V2. We'll do something more with those, but we are looking for those for now. So I could substitute this in here. I could say that I have 15, making my substitution for V1 as 16 over 10 V2 minus 4 V2 is equal to 200. I've just flipped that equation. So V2 turns out to be equal to what? I've got V2 times 15 times 16. I could say it was what? 15 over 10 is 1.5 times 16 minus 4, which is equal to 200. So V2 turns out to be equal to what, 20. So 200 divided by 20, which gives me 10 volts. Let me check my notes here. Yeah, 10 volts. Okay, so then what I could do is I could run over and put that into there. So I'd say V1 is equal to 16 over 10 times 10 volts, which gives me that V1 is equal to 16 volts. Okay, V1 is 16 volts. Good. So we got our node voltages. We found the voltage here. We found the voltage there. What could we do with that? Well, we could say that the power in the 5 ohm resistor, that's what we're looking for, is equal to, I mean, there's a variety of equations we could do. I mean, in general, power is equal to I times V. It's also equal to V squared divided by R, and it's equal to I squared times R when we combine Watt's law and Ohm's law in our work previously. So if I've got the voltages, I could probably do that directly. So the voltage across there is just the difference, and I don't have to worry too much about whether it's V1 minus V2 or V2 minus V1, because I'm going to square the thing. So the difference between those is what? 6 volts? So I have 6 squared, and again, I'm being very careless with whether I'm looking at the voltage there or whether I'm looking at the voltage going the other way, this voltage like that, because I know that I'm squaring it. So I'd have the voltage squared divided by the resistance, which is 5. So this turns out to be, what, 36 over 5, which I think is what, 1, let's see, 7 goes in there a little more than 6, 7.2 watts. Double check that with the calculator. I think that's correct. Yep, 7.2 watts. Now, if you didn't like that, didn't like being a little careless on the voltage there, we could come back and use our old friend I squared R. I like that one. We're first going to have to get I, which the current then is the current through this, I phi. So what do we have for I phi? We knew I phi was V1 minus V2. V1 minus V2 over 5. So we've got that as V1 16 minus V2, which is 10. Over 5, so it's 6 over 5. So I could say then the power in the 5 ohms is equal to, what are we going to have here? 6 over 5 squared times the resistance of 5, which is 36 divided by 25 times 5, which is the same math as that one. Shouldn't surprise us. It's 7.2 watts. Okay, 7.2 watts. Now, if I wanted to get it as equal to current times voltage, I could say that I have 6 over 5 amps. That's where this one came from. Times the voltage of what do we have? 6 volts. So we have 36 over 5, again 7.2 watts. So lots of ways to get that, but none of them would be possible without doing the node voltage method, without coming up with this node voltage V2, without coming up with that node voltage V1. Okay, so The electrical portion of this problem is really right here, writing Kirchhoffs law and making your substitution for voltage, writing Kirchhoffs law and making your substitution for voltage. Then much of the problem just becomes algebra and grinding through that. So practice, practice, practice is my encouragement to you. Let's try another problem. This would be page 2. So in this problem, I'm running a little uphill there. I guess that's okay. I'd like to find the node voltages. So I'd like to find the voltage here. I'll say that that is node number 1. And the voltage there, I'll say that's node number 2. So we can call this V1. We can call that V2. You might say, well, this is a node down here. Well, yeah, if it's a reference ground, what's the, and we always take one of the essential nodes as a reference. If I've taken, and you could take this as a reference, although I think there's some benefit in, out of habit, always just taking your reference down here and then everything is above that. If you want to mix it up, if you get really good at this and you want to play with this, put your reference up there and you'll get the same answers. But if our reference is down here, the voltage here is at the reference, so it's 0. The voltage here is then above that reference, so it's the voltage here with respect to that reference. Let's throw some currents in here. We could put maybe I1, I2, I3, and I4. Okay. And if I start out with Kirchhoffs law here, I mean, maybe I could use Kirchhoffs current law at node number 1. What's that look like? I got I1 going in, and I've got I3 going in. That's what's going in. Has to equal what's going out. I2, right? Can you tell me about I1? What's I1? Let's see. We take some voltage difference and divide by resistance, don't we? I mean, I2 is easy. I mean, you'd say that I2 would be what? It's a voltage across here, which is V1 divided by the resistance, 25 ohms. But I1 is tricky. There's no resistor. And really, you don't need to do any of this, because it's easier than that. Some of you might have spotted this already. V1 is equal to what? V1 is equal to 100 volts by inspection. We'll actually have a name for this. We call this a supernode. We're probably going to concentrate that on a slightly different context. That's when the voltage source is up here. But technically this would be a supernode. But in this case, if you have your voltage source between one of your nodes and ground, it's really easy to figure out what that node voltage is. It's the same as the voltage source. I mean, if I ask the question, what's the voltage across here? Everyone would say 100 volts. So then across here and across there, that's in parallel. So we know that it is the same. Now if there were a resistor in here, it's a whole different story. Whole different story. Just like this one here, I think on this problem. Was V1 20? No, because there was a resistor there. But over here, no resistor, so V1 has to be the same, has to be that 100. So this problem just got a whole lot easier. I got this. I'm only going to need one more equation. I mean, you could say that, yeah, this is still an equation, and I agree with you. But I only have one, shall we say, more difficult equation. So let's do this. I got Kirchhoffs current law at node number 2. What's that look like? You got I3 and I4 leaving. So I3 plus I4, that's what's leaving. That's leaving the node. That's leaving the node. What do you have going in? You got that 5 amps going in, don't you? So this has to be equal to 5. Okay, so I can talk about I3. What's I3? I got to find the voltage that's opposite that, because the current's going to the left, so I got to find my voltage potential to the right. So that's going to be what? V2 minus V1. Minus V1 plus V2, or head minus tail. V2 minus V1 divided by 10. plus I4. I4 is easy, you just have to find that, which is V2 divided by 50. This is probably where seeing this on video is hopefully easier than seeing it in real life. In real life, I'd put that arrow in there real quick, and I think people are heads down writing in their notes. But back this up, really concentrate. If I'm looking for this current I4, I want to find the potential that is opposite that. So that's going to be the potential from there to there, by definition, is V2. So V2 over 50 is equal to 5. Why don't I multiply this thing then by 50? When I do that, I've got 5V2 minus 5V1 plus V2 is equal to 250, right? So I've got then minus 5V1 plus 6V2 is equal to 250. I'm sure glad I got this equation down here so I can substitute this in. So I have, then I'm going to substitute that 100 into here. So I've got minus 500, so it goes over as a positive. So I have 6V2 is equal to, 750? So V2 turns out to be equal to, what, I think 125 volts. Double check that. Yep, 125. So I got 125 volts. So we got this one by inspection. This one, we had to go through more work, and I'm glad we had that V1 because that came important. It was important that we knew that so that we could apply that into this equation. So we found the node voltages. We could go on and find some powers or something like that, but in finding the node voltages, we've got that. We got V1 by inspection. Then we wrote Kirchhoffs, using Kirchhoffs current law up here, wrote the current equation at this node here, made our substitution for V1, and figured out what V2 is. So V1 is 100 volts, V2 is 125. Well, when we get together next time, we'll talk about what happens when we have a voltage source that's up here between these two nodes. A voltage source here, you see, initially might have stymied us or made it more difficult, but we saw that it eventually made it quite a bit easier. We could just recognize that. When we get up here, it's also probably going to make it easier, but we're going to have to deal with it carefully. So we'll go and talk about that in a more formal case of the supernode when we get together next time. So take care till then, and thank you for watching.